With this video, we begin activity 15, which has to do with quadrilaterals and their properties. This is for lesson 15-1, kites and triangle midsegments. Learning goals are to develop properties of kites and to prove the triangle midsegment theorem. Mr. Cortez is the owner of a tile store, and he wants to create a database of all the tiles that he sells. All of his tiles are quadrilaterals, but he needs to learn the properties of different quadrilaterals so that he can classify the tiles in his database. Mr. Cortez begins by exploring convex quadrilaterals. The term quadrilateral can be abbreviated with the word quad. So here we have a sample convex quadrilateral, and question A says list all pairs of opposite sides. So that would be segment GE and segment MO. Those are opposite from each other, and GM and EO are opposite from each other. Question B, list pairs of consecutive sides. So GE and EO, EO and MO, MO and MG, and MG and GE. So these questions are getting at the idea of what's opposite mean and what does consecutive mean in a four-sided figure. Question C asks for opposite angles. They are listed in purple. And question D is asking for the consecutive angles, and they are listed here. Question E, draw the diagonals and list them. So diagonals are segments drawn from one opposite vertex to the other opposite vertex. So there is diagonal EM or ME, same thing. And here is diagonal GO. So drawing from opposite corners creates diagonals. We have ME and GO, and those are listed here. A kite is a quadrilateral, so that means it's a four-sided shape with exactly two distinct pairs of congruent consecutive sides. So it has two pairs of congruent sides. In this example, this is congruent to this, and this is congruent to this. But they come in pairs and they're distinct from each other. Not all four sides are the same length, or that would not be called a kite. That would be called a rhombus. Now, number two, given quadrilateral kite with these congruent sides, question A, one of the diagonals divides the kite into two congruent triangles. Draw that diagonal. So is it the one from here to here? Does that make congruent triangles? Or is it the one going across from K to T? And it is segment 8 KT, making this top triangle and this bottom triangle. It says list the congruent triangles. So we would have triangle KIT, and that is congruent to triangle KET. How do we know they're congruent? By side, side, side. We have the mark in this mark, the double mark with that double mark, and then the shared side is certainly congruent to itself. In a past lesson, we would put that symbol on there to help us see the SSS criterion. Question B, draw the other diagonal. Okay, here it is, going from I down to E. Explain how you know the diagonals are perpendicular. How would we know that that's a 90-degree angle box? The explanation might go something like this. Because this diagonal created those original congruent triangles that we had indicated, we know that this angle was congruent to this angle because corresponding parts of congruent triangles are congruent. We know already that this side here with the single tick mark is congruent to that side. And then looking at this short segment here, it's being shared between this triangle and this triangle below. It's congruent to itself. I'm going to mark that with a little X. So we have kind of like side, angle, side here to explain why this triangle is congruent to this triangle. Because those triangles are congruent, then we know that this angle must be congruent to this angle, again because of the corresponding parts of congruent triangles are congruent. And if we have two equal-sized angles that create a straight line, then they must be a linear pair, and they have to be 90 degrees. So that's why we know that they're perpendicular. Question C, complete the following list of properties of a kite. Think about angles as well as segments. So some of them were already typed there for us, some things that are true about kites. Exactly 2 pairs of consecutive sides are congruent. 1 diagonal divides the kite into 2 congruent triangles. That was the first thing that we had drawn above when we drew across the middle there. Third thing that's true about kites, the diagonals of a kite are perpendicular. And then here's a few more of them that I listed in purple. The other diagonal divides the kite into 2 isosceles triangles. The picture's a little bit sloppy now with all the brown writing on it, but this diagonal that was drawn downwards, it creates an isosceles triangle here, and then over on the right, it creates an isosceles triangle. Another property that's true, 1 pair of opposite angles are congruent angles. And then something else that's true, one of the diagonals bisects a pair of opposite angles. So these 6 statements are all true properties of kites. Number 3, Mr. Cortez says that the diagonals of a kite bisect each other. Is he correct? The answer is no. Let's make a quick counterexample to show why he's incorrect. Here is a kite, and if we draw the diagonals across here and here, this diagonal is bisected into equal pieces. But the longer diagonal, I hope you agree, is not bisected into 2 equal pieces. Here are some check your understanding questions, so I'll pause the video. We're going to change pace a little bit now and go back to the triangle shape instead of looking at the quadrilateral that's called a kite. The segment whose endpoints are the midpoints of 2 sides of a triangle is called a midsegment. Here's the triangle midsegment theorem. The midsegment of a triangle is parallel to its third side, and its length is half the length of the third side. Here we have a triangle called triangle ABC. Point M is located as the midpoint of that side. Point N is the midpoint of that side. So this segment, MN, is called the midsegment of triangle ABC. We know that that midsegment is parallel to that third side, and we know that the length of that brown line is half the length of that third side. That's what the triangle midsegment theorem is telling us about that midsegment. Okay, now it asks us to prove that theorem. So the hypothesis is to show that M is the midpoint of AB. N is the midpoint of, and I filled in BC. Let's show that MN is parallel to AC, and let's show that length MN is half AC. Question B, find the coordinates of midpoints M and N in terms of these variables, because these are the variables that are used in the ordered pairs. So I've used the midpoint formula to find the midpoint M. We add the x coordinates of A and B and divide by 2, and add the y coordinates of A and B and divide by 2. That creates this expression. Similarly for N, we add the x coordinates of B and C, divide by 2, add the y coordinates of B and C, and divide by 2. So I know these expressions look a bit weird, but that's what you get when you take the different variables in the ordered pairs and put them into the midpoint formula. Question C, find the slope of segment AC and MN. So to do this, I've used the slope formula. Does the slope formula look familiar to you? It's over here in the green box. Subtract the y coordinates to find the rise. Subtract the x coordinates to find the run. Rise over run. Does that formula look familiar? Again, we have variables instead of numbers to fill into these positions. When you fill in those variables, the slope of AC turns out to be this expression, and the slope of MN turns out to be that expression. Question D, simplify that expression to explain how this slope is the same as this slope. So the first thing I did, because all four of these fractions have a denominator of 2, I multiplied the top and the bottom by 2. That canceled out the denominators and left this expression here. Then I did the subtractions, and that created L minus H over C minus A. Please notice that this is the same slope as we had for segment AC. So this demonstrates the slope of MN is the same as the slope of AC. They are parallel. Question E, find length AC and length MN. So to find lengths, you use the distance formula. So over here in the green box, does that distance formula look familiar? Where you have a large square root symbol and then you subtract the x's squared plus subtract the y's squared. Again, what you're putting into these positions are variables from that drawing instead of numbers. So that's going to create some algebra expressions with variables. So length AC turns out to be this right here, and length MN turns out to be this expression over here. Question F, simplify that complicated looking one to show that it is half of AC. So the first thing I did is I did the squaring part, and the denominator of 2, when you square it, turns out to be a 4 here and here. Then I did the square root of this. The square root of the 1/4 part makes 1/2 pulled out at the front, and then the other stuff I left in the square root. Notice how that expression in the square root is the same thing as AC. And so we have shown with algebra that length MN is equal to half length AC. Here are some check your understanding questions, so I'll pause the video. In this lesson, we discussed a four-sided figure called a kite and looked at some of the properties of the kite, mostly involving diagonals of the kite. And then, for some reason, a triangle was put into this activity as well, and we looked at the triangle midsegment theorem.